right, good morning, everyone. Welcome to another edition of the Finite Element seminar at Lawrence Livermore National Lab. Today it's our honor to have as speakers from the Polytechnic University in Madrid, Professor Esteban Ferrer and David Huergo. They are going to both present part of this talk on the spectral digicode and some interesting things they're doing with machine learning recently. I heard part of this at ECOMAS, and I thought it will be interesting for this community to hear more and to form connection with them. So I was very happy that you guys agreed. And please, Esteban, take it away.
Well, thank you very much for the invitation. So in the first part of the talk, I will be talking about a little bit of the overview of our solver, the solver we're developing, which is a discontinuous Galerkin solver, and some of the add-ons we are keep adding to the solver. And in the second part of the talk, my PhD student, David, he will be presenting some reinforcement learning coupled with our solver, with our high-order solver, to do mesh adaptation and particular mesh adaptation. So I'll start so I can give some time to him in the second half. So first I need to acknowledge all my students and the funding, of course, from ERC funding, European funding, and also national funding. Also acknowledge some collaborations with industry that we have these days with Airbus, McLaren, and Siemens Gamesa for wind turbines. And now I can start with the talk. So I'll start with the summary. And we will start with the introduction of discontinuous Galerkin method and more precisely with high-order method and our solver, which is called Horses 3D. So I will give some highlight of the solver. Then I will talk a little bit about the multiphysics we add into the solvers. And this is because these days we're very interested in wind turbines. So I'll show you some ways of computing wind turbines, a few ideas on turbulence modeling, new ideas on turbulence modeling. And then I'll go into a second part, which is a bit more new or some more crazy ideas, if you wish, where we couple machine learning with CFD. And just to give you some ideas. So we are developing this solver, which is Horses 3D. This is a discontinuous Galerkin solver. It's open source. You can find it on GitHub. We recently wrote this paper where we have some summary of things we can do. And in a nutshell, we can do all these things: compressible, incompressible solvers. We have entropy or energy conserving formulations for increased stability. We can do local p-adaption and very recently hanging knots for h-adaptation. We have explicit implicit time marching, and we have turbulence models of LES types mainly, but we have also a RANS model with palatine mirrors. And then we can do some different multiphysics, including multiphase, immerse boundaries, shocks. And I'll show you some examples of immerse boundaries and shocks, not multiphase in this. Right, so in a nutshell, we can do solve all this variety of problems where we have here a wind turbine with immerse boundaries. I will talk a little bit about that later. We can do multiphase, but I'm not talking about that. We can do shocks, as in this Apollo capsule. We can do acoustics, very interesting acoustics these days, and in particular acoustics of wind turbines. Right, so I'll talk a little bit about that. First, I will motivate the use of high-order methods. So in low-order methods, classic low-order methods, what you have is a mesh made here of triangles, for example, and then you will have a piecewise constant function inside the element to capture the solution. In finite elements, instead of a constant, you have a piecewise linear variation similar to that one inside each element, and that allows you to capture the solution. If you want to increase the resolution, you need to increase the number of elements to get to capture the gradient in the solution. Now, in higher-order methods, and in particular in discontinuous Galerkin, we can do two things. We can increase the number of elements as in lower-order methods, the same idea. That's what we call edge refinement. Or what we can do is fix the mesh, fix the number of triangles, the number of quadrilaterals, and increase the polynomial order inside each element. So instead of using piecewise constant values or piecewise linear variations, we can use quadratic or cubic variations or any arbitrary polynomial order inside each element. And this allows you to better capture the solution whilst keeping the same number of triangles. Now, why wonders why do one or the other, right? Because if you increase the number of triangles or you increase the polynomial, what you're doing is better capturing the solution. Well, I think everything can be seen in this very simple problem. This is a Poisson equation, so an elliptic problem. We have here the L2 error, right? So that we know the exact solution. We can compute the error between our numerical solution and the exact solution. And here we have the number of degrees of freedom used to solve the problem. So this relates to the size of the matrix we need to invert to get the solution. So if we use a low order method, let's say we fix the polynomial to order 2, right? The boxes show the polynomial order we use. The only way to increase the solution is to add more elements, right? So that we go from 32 to 128 elements, and then the error decays like this, following this line. So we would say it decreases slowly. Of course, it decreases the error, but slowly. The alternative is to use a high polynomial order with a coarse mesh. So we can fix the mesh to 32 triangles. This is the red line here. And when we can increase from P2, polynomial 2, to P6, for example, right? We see that the decay in the error is much, much faster. So basically what we're saying is that if we are interested in a particular level of accuracy, let's say 10 to the minus 7, we can use a polynomial order 6 on a coarse mesh, and that leads to 1,000 degrees of freedom. So that's the size of the matrix we need to invert, as opposed to if we use a low polynomial order, we are outside the screen, right? So that means a much larger matrix that we need to invert. So overall, there is a saving in memory and cost because we need to invert a smaller matrix for the same accuracy. So that's the potential of higher order method, right? It can be explained in this simple problem. Again, this is a Poisson equation, very simple problem. So what happens if we go to more complex stuff? So if we compare, for example, a higher order method, P5, on a very coarse mesh as this one, what we see is that we capture well the structure of the flow after an airport in this case. However, if we use a lower order solver, this is a finite volume solver, it answers a particular fluent, what we see is that we get dissipated structures very soon after the water shedding starts. And this is due to numerical errors, and these numerical errors relate to this low accuracy or lower accuracy for the low order solver. And this is on a much finer mesh than for the higher order solver. So overall, when we go to practical applications, we do see the effect of this improved accuracy for high order polynomials. I have another example, which is even more complicated, and this is the acoustics emanating from the trailing edge of this airport, right? So the acoustics in this case is complicated. You have to very well capture the boundary layer and the vortex shedding emanating here at the trailing edge. Those vortices interact with the shear layer here at the trailing edge, and there's some waves emanating and going up to the front, right? So then what we're doing here, let me just get the things. Sorry about that. So what we're measuring here is the acoustic pressure at this particular point. So we need to well resolve the near boundary layer and also all the propagation of these waves throughout the space up to this point. Right, so if we do that and we increase the polynomial order, what we see is what looks like a random signal. We're not sure if the increasing the polynomial makes really sense. But what we can do is take this signal and integrate it from 0 to 20, and then we can get an integrated value for the overall some pressure level against the degrees of freedom. And what we recover is this very rapid decay of the error. So very similar to what we were getting for this analytical elliptic problem, the very simple problem. This is much more complicated. We have generation of noise, we have propagation of noise. And as you can see, when we do direct numerical simulation of the noise, we lose a little bit of the accuracy. We think this is because of these reflected waves that we get from the boundaries, right? So we're working on getting rid of that. But overall, we get very rapid decay of the error. We get exponential decay of the error, similar to the elliptic problem, for more complex problems than just an elliptic problem. Then, of course, the big question is, well, okay, the error decreases very rapidly when you increase the polynomial, but what happens with the cost? Because if the cost increases exponentially, then you don't gain anything, and you will be right. Now, we have checked that in our solver. This is parallelized. This is a few tricks to improve performance. And what we see is that when we increase the polynomial, the cost increases linearly, roughly linearly, not exponentially, right? So we get exponential decrease in cost, in error, but only the cost only increases linearly, which makes it very advantageous to use high polynomial orders, right? So this is what we typically do. We use polynomial order 5, something like that. Right, so very recently we have ported the solver to GPUs. So this is a first, it's on the way. So we're trying with OpenACC to port that to GPUs. And what we're seeing is we're getting, when we compare to 100 CPUs, we get in one GPU NVIDIA 100, not one of the very good ones, we get per iteration at a reduced cost of 0.07 seconds. And one can play around with this number and say, okay, for an LES simulation, it's not strange to have to run 10 to the 8 times that or something like that, which basically means that you get 81 days faster computations with one GPU than with 100 CPUs. So we are happy. We are keep improving this. We have more ideas on how to keep improving this. We're doing it. Right. We have coupled in the past horses to FEM, to other solvers, in particular FEM. And I have here a couple of snapshots of what we've done, and this to get the conversation going with you guys. So one thing we have done in the past is solve the fluid with horses and solve the thermal part of the problem, which is this capsule Apollo with FEM. So we were coupling, the two-way coupling of the temperature from one to the other. A second example of things we have done in the past is solve some incompressible, so develop an incompressible solver where we need to solve a Poisson equation and a Helmholtz equation. This is one of the splitting methods to solve the incompressible Navier-Stokes equations. And then some parts we're using FEM because basically we don't have a CG, a continuous Galerkin solver. We only have the DG and flux reconstruction versions. So some parts we're using CG with FEM and some parts we're using DG. And this we did in a PhD thesis of one of my students a while back. Right, so I think we have done that in the past. We know how to do it, and I think that allows us to think of interesting ideas of solving different parts of problems with FEM or horses. Right, so let me go into some of the physics we are developing or including in the solver these days. Right, so we're very interested, and this is related to an ERC grant that I got recently, a lot of wind turbine simulations. So we do simulations with immense boundaries, with actuator lines, and also looking at the interactions of one wake with another one, with another wind turbine. So all these things are in development now. So if you want to model or simulate wind turbines, there's different ways of doing it. You can use actuator disks, actuator lines, immense boundaries, and sliding meshes. So we are working in all of those. Actuator disks are very easy, just pressure jump in your simulation. So I'm not going to talk about that. That's too easy. I'm going to talk a little bit about some recent developments on actuator lines, immense boundaries, and sliding meshes. So let me start with actuator line. So the actuator lines, it's a very neat idea, right? Because what you do is you get a simulation of two-dimensional airfoils, or you can get it from X-foil or whatever. You only need the lift and drag coefficients on this. Then you get these formulas using the velocity in your CFD flow field to calculate the forces, and the forces are calculated for each section of your blade, and then you can add this forcing into your simulation, right? So you don't need to simulate the whole geometry, but you only add a force, a point with a force with the lift and drag in the direction needed. What you do is you smooth these forcings to avoid a sudden peak that would blow up the solution. So you use a Gaussian to smear this force. And then you can do the smearing and everything in high order. So I'm not going into the details here, but that can be done. That's not difficult. Right? I want to talk about something else. So when you use these techniques, you can see this kind of behavior. When we have polynomial order 2, we have a very not clear surface, but when we increase the polynomial, we get the right structure, right? We get the right T-vortex formation and everything, as expected. Right? When we compare our solutions, that's P2, P4, we have P5 and P7, but sorry, I haven't updated this presentation. And we compare with a finite volume method, which is very, very fine. This is open form with 190 million elements. We see very similar results, knowing that with P4, we're using 10 million, roughly, degrees of freedom, as opposed to 190 million. Right, so it's 15 million, 10, 15 million compared to 190. So again, here we see the effect of having this high order polynomial really helps in decreasing the cost, or the number of degrees of freedom we need to solve. Now, of course, these ideas the actuator line ideas were all developed for low order methods, for finite volumes in particular. So, and this is an example of the things you need to think of when you adapt things from low order to higher, right? I think. So the way this works, I repeat, you have the lift and drag. You get the u velocity squared, this one here. You take it from the CFD simulation, right? And with this, you compute the overall force. So this guy here. So, of course, something natural to do in low order methods. When you check one cell, you have only one value for the u velocity. So you take that value and you compute. So this is the average value in the cell, if you wish, and then you compute the force, and that's it, right? So this is one of the options. You can take, in high order, what you have is one big element and a lot of Gauss points inside this element, right? So what you can do is take the average of the velocity in all these points, and you have one unique value, average, for the whole cell. And with this, you compute the forcing and you carry on. That's very similar to the low order solution. Perhaps a more high order idea is to do some weighted average, right? So you can take the forcing, compute the local forcing in each Gauss point, right? And do some weighted average of these local forcings, which is weighted by these Gaussians as well. Okay, so this is a bit more weird idea. Then we have tested both. What we observe is when we do the cell averaging, this is when we do cell averaging or weighted average for low polynomial orders, we get almost exactly the same flow fields. So we don't see anything in particular. Of course, that's low order, and that makes sense that they're similar. Now, when we go to high order, P5, we see different physics. So what we see is that with the cell averaging, we are changing the physics here, we're getting these oscillations, these long wavelength oscillations here that we don't get with the weighted average, and we don't get when we have very fine simulations with finite volumes. So the message here is one has to be careful when he adapts things from low order to high order, because it doesn't always work. Sometimes you have to rethink things. Right. You might wonder why we don't get the right results when comparing to the experiments. And this is because in these cases, we only had the actuator without the tower, because we wanted to see really the effect of this implementation. But when we include the tower and the nacelle and everything, such as in these cases, we get quite the right wake. So very similar to the experiments. Right, so this is one possibility. Second possibility is to use inverse boundaries. What are inverse boundaries? So inverse boundaries, you have a mesh, a Cartesian-like mesh, something very simple, and you modify your Navier-Stokes equations to add some penalization, some penalization term that drives u velocity to zero in all these Gauss points inside your mesh. And that mimics the effect of having a body. The nice thing of this is you can use Cartesian grid. You don't need to body fit your mesh. You can have complex geometries and moving geometries very easily. Right? And again, from a CFD practitioner, no meshing is very nice. Right? I don't think anybody likes meshing. So, well, this is what we get, right? So we can move things around very easily, and we get quite the right results. For these cases as well, there's a bunch of papers that we developed here a couple of years back, where we analyze the errors and we analyze how we can improve a little bit the method and everything. One of the interesting things that we found is that when you increase the polynomial, you do get better solutions. So you do get this kind of exponential convergence, this very rapid decay of the error when you increase the polynomial, which was not obvious because of this way of imposing the boundary conditions. But it can be done. And we've recently developed a high-order version of the immersed boundary as well, which can prove that you get the very right high convergence. Right. So having that, we can do wind turbines as well. So for this, we use only the STL and a very simple Cartesian mesh. The solver, we define all the points that need to be penalized, so all the points inside the body, where you need to add this additional source term. And then we can run this kind of simulations. Here, for example, in the wake, I use a high polynomial order. In the far field, low polynomial order. What we see is that, of course, there's no solid, because there's no solid. But we can always overlay the CAD file to see that we're getting things right. Right? So in this case, the blades are rotating. And what we see is that the right physics are right? So we get the seed vortex, we get the leading edge acceleration of the blade, we get the tower, we get everything. So typically what we do these days is we use actuator lines for the blades because it's cheaper. And then we use mesh boundaries for all these things. But we also sometimes move things around and get these with mesh boundaries. And finally, the final possibility is to use sliding meshes. And basically, sliding meshes with high order was part of my PhD back in the days. And here you can see that the inner mesh rotates, the outer mesh is static, and you get a sliding interface here. The interesting thing is that the contours go through the interface and they don't care there's any interface, right? So they just get affected. There's no spurious oscillations or anything. And you can ensure that by doing over integration when you have high order methods. Right, so this is a bit more costly than the previous ones, but it can be done. We have done it, and we're now implementing it in horses as well. It's not there yet, but it'll be there soon. Right. I think I'm going to skip a little bit the turbulence part, because otherwise I'm going to run out of time, and I'm going to talk about the machine learning ideas. Right. So let me just skip that part and go into the machine learning. So things that we're doing in machine learning, we're trying to couple, I call that AI-based CFD. So the idea is to get some of the features of AI and try to improve the CFD simulation, right? So we've been thinking, and we think there's three things that can be improved. So one is the efficiency of the solvers, the accuracy can be improved, and also automation of the CFD. So for automation, David is going to be talking about reinforcement learning. We can automate some of the things we typically do by hand or something with CFD. Efficiency and accuracy, I'm going to be talking a little bit now. Right, so one of the things one can do is regarding accuracy and efficiency is to try to use the high polynomial order only in the regions that are needed, right? So typically feature-based sensors for adaptation to improve the solution require some threshold. So for example, if we use the eddy viscosity sensor, which takes into account the whole turbulence of the flow, you need to set a threshold like the contours. When you plot contours in ParView or in TechLog, you need to set a threshold for plotting. And this threshold makes the region vary a lot, right? So if you use 1.25, you get this red region. If you change the threshold to 1.5, you get this region. So this is not ideal, right? Because the using high polynomial or not will depend a lot on this threshold, which is arbitrary. So what we have done, so it's very sensitive to the threshold value, right? And also it's difficult to get mixed regions, right? So here you have this blue region here that probably you want to adapt because it's in the wake of the cylinder, but it will be missed with this eddy viscosity sensor. This is a laminar region. There's no turbulence here, right? So we weren't really happy with this feature-based things, so we tried to use clustering, right? So clustering, as you can see here, allows you to detect regions in your flow, and in particular, we use Gauss mixture models. There's a bunch of different ways of doing it. We use that one. So if you use the right feature space, so for example, we use vorticity and strain rate, you throw that into a clustering, and the clustering, which is a machine learning based idea, you tell him, give me 2 clusters only, it will give you these 2 clusters, right? So one cluster where there is a lot of strain rate and rotational stuff going on, and one where there is almost nothing, right? So if we use those to perform adaptation, and there's no thresholds here. The important thing is there's no thresholds. You tell him two clusters, it gives you 2 clusters. So we can check if what we're doing is right. So for example, we check the cluster-based adaptation from P4 to P2, and we compare that to a uniform refinement of P4, and we see that the values are almost identical, right? So we are getting almost exactly the same solution. This is turbulent flow field in weight, but with a reduction in cost of 33%, a 40% reduction on degrees of freedom. So we have tried this idea for incompressible light flows, so very low max turbulent flows, and wind turbines as well. We get very similar results. So the idea is with these 2 clusters, what we do is we get the interesting part of the wake, right? And this is the thing. So we have a various papers showing that. We have applied this technique also to shocks, because with horses we can do shocks. And what we see is that if we use feature-based, again, we change the threshold and so here to capture the shocks, it changes a lot the definition of these shocks with the threshold. However, when we use the GMM, the Gaussian mixture model, what we see is on no tuning, there's no thresholds, and we get the shocks quite all right. And we get, so that's the idea. So if you want to see here, then of course, if things evolve with time, we can do the clustering every so often, reinitializing from the old one, so it's not that costly, and then we get the good tracking of the shocks. Right. So all these ideas came out in a few papers. We have 1, 2, 3, 4 papers on these techniques, and we think it's reasonable. Right. So David will talk about using reinforcement learning for adaptation, which is a different idea, and he will talk about that in like 5 minutes. So I think I still have 5 minutes. And in this 5 minutes, I would like to show you a little bit of another crazy idea of using high order with machine learning. And this looks into the efficiency of the solvers. Try to accelerate the solver without losing accuracy. Right. So if we think of low order methods, low order polynomials, and high order polynomials, one of the things that happens is that with low order methods, you can use very large time steps. Right? But with high order, because of the CFL condition that links space and time, you need to use smaller time steps. So basically, the solution advances very accurately, but very slowly. Right? So wouldn't it be nice if we could run a low order polynomial, so very badly resolved simulation, and every so often or every time step correct it such that we get the same solution as the filter high order solution. Right, so that's the basic idea. So if you want to pose that problem, what you do is you write the evolution equation for the low order problem, you write the evolution equation for the filter high order, and those guys are completely different, of course. This guy is okay, it's accurate. This guy is completely crap. Right? and you think what's missing here for one to match the other. So then you can think of different ways of doing it, but the way we thought is adding a source term here to the low order equation that now we call the neural network equation. We'll soon see why. Where we correct the low order solution, this one which is crap, to get the filter high order solution. And we do that for every single Gauss point in our mesh, right? So they all get corrected with different SN. So where is this SN? Well, we call it neural network, so obviously it comes from a neural network, right? So what we're going to do is we're going to train a network to get us this correcting forcing based on some training window. During some time, we're going to train with high order solutions to get us this SN. And after this window, we're going to forget about the high order and we're going to keep correcting the solution with this SN. So to check this idea, we did it first. We postulated this idea in 1D for Burger's equation. So very simple. We had a paper in computational fluids from that. And later we used it in 3D for turbulent flows in this JCP paper. So that was my bad idea to use the Taylor-Green vortex to start with this, because the Taylor-Green vortex, I didn't realize at the time, it's very complex in terms of the physics, much more than one could think. Of course, it's a box and periodic boundary conditions, and one thing is simple, but physically it's not simple. You have a laminar flow, a transitional flow, and a turbulent flow, right? And everything happens in this box. So when you want to try to guess things, well, you have various regimes, and they are not the same. Right. So what we did is, again, we took a very small window like this, and we train with we run a p8 solution. We run a p3 solution. The low order solution runs 3 times faster than the p8 solution. Right? And then we train in this window, and then we're going to keep correcting with the source term that we obtained here after the training. Right? And this is what happens. So we can check the difference between the p8 solution, the filter p8 solution, that's the good one, minus the original p3 solution, that's the bad one. And we get this curve here. So that's the one to beat. And then we have the p8 filter minus the p3 plus supplemented with the source. Right? What we see, first of all, is that we improve the solution. This is good. The error decreases, so we're getting closer to the p8. Another very interesting thing is that we get improvements during training. Okay, that's fair enough. During the training, we have data and we get an improved solution. But what's more interesting is that after the training, we keep improving the solution. So this is still lower, and it's still lower for a while, right? So this is the real magic, because in this region, you don't need the p8 solution anymore, right? You have the p3 plus the source term, and you don't need the p8 solution. Now, if we were to compare p3 plus neural network to the p8, we will get 12 times faster times in the solution, because p3 plus neural network is much faster than running a p8 solution. So there will be accelerations, but there's a trick. And the trick is that we're not getting the p8 accuracy, right? If we were to get the p8 accuracy, we will have a curve that it's down here, and we are not. We are losing something. So we are improving the p3, but we're not getting to the p8, right? So to see what actual polynomial we are getting, what's the real accuracy of the p3 plus neural network, we can run a bunch of different simulations from p3 to p6 and compare the p3 plus neural network. And what we see is that more or less we get a p6, p5, p6 solution. Now, if we compare the p3 plus neural network with the training and everything, compared to the p6 solution, we get a 4 to 5 times faster solution. So we are indeed improving the efficiency of the solver by mixing with this. Finally, I'm almost there. We try for one particular window. We try here, okay? That was laminar transitional. Transitional, I would say, laminar complex. So we try for different flow regimes. We try for laminar, transitional, turbulence, and more turbulent. And what we see is there's always improvement. So the method kind of works all the time. Doesn't matter if it's laminar or turbulent regime. It works better or worse depending on the regime, but it always gives you some improvements. But more recently, we have tried different neural networks, so fully coupled CNNs and LSTMs, and we can get some additional improvement over what I just showed. Okay, so there's room for improvement. It's not super massive, but you get some improvements. Right, and with that, I go to the last part, which is going to be automation of the CFD. And this is going to be explained by David. So the idea here is to use reinforcement learning that allows you to automate processes or play games, win at games, like Go, chess, Atari, etc. So now our game is the CFD simulation, and we're going to compete with the reinforcement learning some stuff. David's going to talking about that. Let me just show you something that I think is not going to be covered by David. David's going to be talking about adaptation. Well, another things we've been doing recently, it's getting the right parameters for multigrid. So in multigrid, you have a bunch of different parameters. And what you do is, if you have a student trying to run the simulations with multigrid, when the advection speed changes, this is 1D, or the viscosity changes, the parameters in the multigrid change a lot. So this is the strips and the relaxation between levels that you use. You have to fine tune this, and you get your student completely crazy trying to tune these things. And sometimes it blows up. All these, depending on the parameters you use, it blows up or it works. So these are what my students did. So what you do in these cases, you use reinforcement learning to choose the parameters. And after a random initial test from the reinforcement learning, it gets eventually to the right parameters, which is around here, right? And so when we compare the reinforcement learning results to the student, meaning the arbitrary is the student trying random stuff, we always get a better runtimes than with the student setting. So that's very promising. And now I'll leave the room to David, who's going to be talking about reinforcement learning for p-adaptation. So you can go ahead and share the thing. I would just leave this slide just to mention that we have openings in our group. So if anybody's interested and you like computers, fluids, wind turbines, like Bill Gates in this case, it don't have to be that much, but just come and write me an email. Okay, so with this, I'll leave room to David.
Okay, thank you, Esteban. I hope you can see my screen.
Yes.
Okay, thank you, Tania. Well, thank you everyone for attending this meeting. I'm David Huergo, and I'm a PhD candidate, and Esteban is my supervisor. And my field of interest is the use of reinforcement learning just for improve and to speed up our CFD code. So in this presentation, I want to show you how to use reinforcement learning for anisotropic p-adaptation and also for error estimation in high-order solvers. Well, as Esteban said before, this research is funded by an ERC grant, and our main objective is to analyze offshore wind turbines so that we can minimize its acoustic footprint and also to protect marine life. But to do that, we need to run a lot of simulations with wind turbines and different strategies and methodologies. And so we need faster solvers and more accurate solvers. So that's our motivation, and that's why we want to use reinforcement learning to improve our code. So these are the contents of my presentation. I will start explaining the basic idea behind p-adaptation and a brief reminder of discontinuous Galerkin solvers. Then I will move on to the use of reinforcement learning for p-adaptation, and finally, I will show you some results, the ongoing work, and some final conclusions. So first of all, what is p-adaptation and inside the discontinuous Galerkin solvers? Well, DGSM, as Esteban said before, is a finite element method in which we can approximate the solution inside each element of our mesh using Lagrange polynomials. And these polynomials are based on Legendre-Gauss nodes. And of course, the solution can be discontinuous between elements. Within this framework, the use of p-adaptation allows us to select the optimum polynomial order inside each element of the mesh so that we can obtain accurate solutions in those regions of interest, but also to reduce the overall computational cost. So the idea behind p-adaptation is very interesting, but we cannot do it manually because the task to select the polynomial manually is highly time consuming. So we want to do p-adaptation, but we want to do it automatically. In our research group, we started with p-adaptation, and we used the truncation error as a measurement to decide where to increase or decrease the polynomial order. In fact, we implemented this strategy in our solver, the one that Esteban told you about, and we discovered that, in fact, the use of p-adaptation allows to drastically reduce the number of degrees of freedom, so we obtain a huge speed up. The problem with this approach is that the computation of the truncation error itself is highly time consuming. So we want to use p-adaptation because it has lots of advantages, but we want to use reinforcement learning to speed up the code because the truncation error is not as good as we expected. So how can we use reinforcement learning for p-adaptation? Within the reinforcement learning framework, there are two main blocks. The first one is the environment. That is the problem that we want to solve. In this case, the environment is our discontinuous Galerkin solver, the solver that we will use to solve our equations. And the other major block is the agent. The agent is the brain behind the reinforcement learning. And the agent will receive information from the environment. That is what we call the state. And then the agent will generate an action. In this case, the actions are going to be to increase or decrease the polynomial order inside each element so that we have that p-adaptation. And finally, we need to define a reward function to tell the agent during the training if it's performing well or not. So the first thing that we must define is the state. This is the most important part. And to define a good state, we must ask ourselves what we need to know to adapt correctly the polynomial order inside each element. Well, in this case, it's quite simple. We just need the flow field, the solution of our variables evaluated at the Gauss nodes. So that's our state. But of course, the size of the state is going to be dependent on the polynomial order that we use. So in different elements, we may have states with different sizes. And then we have to define the reward function. The reward function is the objective function that we want to maximize. But for this problem, we have two opposing objectives, and we must find a trade-off. First, we want to minimize the polynomial order because that means that we are able to minimize the number of degrees of freedom and to reduce the computational cost. But also, we want highly accurate solvers. We want to use high order in those regions that are of interest, where we expect to have a strong gradient. So with that in mind, this is the definition of the reward that we have defined. And there are two parts. The first part will try to minimize the polynomial order, while in the second part, the exponential part, will try to minimize the error or to increase the accuracy. The most important one is the second one, because there's an exponential. And here the agent will try to reduce the error. But once the error is, let's say, acceptable, based on this parameter, this sigma, this alpha, then once the error is acceptable, then the agent will try to minimize the polynomial order to reduce the computational cost. And now that we have defined all the elements of the reinforcement learning framework, we have to train the agent. But we have to face two main drawbacks. The first one is that, as I'm sure that some of you already know, train a reinforcement learning agent is in general very expensive. And it's even more expensive if coupled with a CFD solver. So that's a problem. And the second drawback is that to compute the error in the reward function that I showed you before, we need to know the analytical solution. We need a reference solution to measure the error. And in general, in computational fluid dynamics, we don't know the analytical solution, for example, for the Navier-Stokes equation. So to solve both problems at once, we are going to train the agent based on polynomial functions that we are going to define. And that's going to be our reference solution that we are using to train the agent. Doing that, the CFD code is not required during the training. So we are able to decouple the CFD code and the training of the agent. That means that the training is going to be very, very fast. And also, we know the analytical solution because, in fact, we are creating the analytical solution, those polynomial functions. The resulting agent has to be trained only once and for all. In fact, keep in mind that all the results that I'm going to show you, they are all computed with the same agent. We have only trained one agent, and it's valid for everything. It can be potentially applied to any partial differential equation if solved with a discontinuous Galerkin solver, and you can use it in an arbitrary mesh because the agent is going to select the optimum polynomial order in each element individually. Well, maybe you think that all this explanation of the training is a little bit abstract, so let me show you a brief animation just to clarify how this training works. So imagine that we have an element, and inside you have 4 Gauss nodes. And you may think that there's an infinite possible amount of polynomial functions that go through all those points. So if we need a reference solution, the simplest approach is to fit those points with a polynomial P3, because there's only one. But maybe those points are representing a low-order polynomial. Maybe the real solution is a P2 polynomial. Of course, in this case, we should check that the error between the low-order and the high-order polynomial is small enough to make sure that the P2 polynomial is feasible to represent those points. But it could also be the case that the real solution comes from a higher polynomial, for example, P4. So during the training, we will provide the agent this set of positions for the Gauss nodes. And the agent will have to face all these different scenarios. That way, the agent will be able to learn that for the same set of Gauss nodes, there are several, in fact, infinite possible polynomial functions that could be the real solution when we are trying to solve a real problem. So given that information, the agent, based on these probabilities, will try to select the optimum polynomial order to minimize the risk or to maximize the benefit that we may obtain even though we don't know which is the real solution of our problem. And finally, well, as you have seen, all this explanation is based on one-dimensional problems. But what if we want to use the same methodology for two-dimensional or even three-dimensional problems? Well, in that case, imagine we have a mesh made of ixahedra, and let's focus on a single element. And inside that element, we have a set of Gauss nodes. So let's pick each row or column inside that element, and that's going to be the state for our agent. And let's repeat the same operation for every row or column of nodes. With all that information, the agent is able to provide an action. But if we do the same for the 3 different axes, X, Y, and Z, we obtain 3 different actions. That's why our algorithm is anisotropic, because inside the same element, we may have 3 different polynomial orders, and in fact, our agent is able to select 3 different optimums based on this approach. And well, before I show you the results, I want to give you just a brief overview of how we estimate the error. Every reinforcement learning problem is based on this equation, the Bellman optimality equation. And it has 4 main variables. The first one, the v-values. The v-values tell you how desirable is to reach a state S. And this equation links the v-values of the present state S and of future states S prime. Also, we have the reward function that we defined before. We have the discount factor that represents how important is the long term versus the short term. And finally, we have a probability transition function that is used in stochastic problems, because from the same state S, there's a probability of reaching a different number of future states S prime. So during the training, we are using a classical reinforcement learning algorithm called value iteration. And during the training, we are able to compute all these variables for every possible situation or a scenario that you may find in a real problem. So we know all these variables. And after some rearrangement and some math, we end with this formula. This formula is the one that we use for the error estimation. And the good point about this is that all the variables inside the equation are known during the training. In fact, we are able to compute during the training an error estimation for every possible situation that you may find in the future. So once you are running a real problem and you want an estimation of your error, you only need to look at the values that you computed before. So the error estimation is very, very cheap, so cheap that it's free. The computational cost is 0. This error estimation provides the spatial error. The temporal error does nothing to do with this, only the spatial error, but it's the error that the agent believes to be real. It doesn't mean that it's the real error, but it's the error that the agent believes to be real. And as I said before, it's learned during the training. Of course, the agent doesn't know anything about what equation you are trying to solve, or what variables you are trying to estimate, or what are the boundary conditions. So this is only an estimation. But we have discovered that though you can use this estimation without p-adaptation, if you couple both, if you couple p-adaptation and error estimation, the accuracy of the estimation is much higher. So I recommend to use both at once, p-adaptation and the error estimator. And finally, I want to show you some results that we have obtained with this methodology. So first, to show you the error estimator, this is a very simple problem, the Euler flow around the cylinder. And on the left, you have the error estimator, and on the right, you have the real error. So keep in mind that the agent doesn't know what equation we're trying to solve, what variables we are estimating, what's the problem that we want to solve. The agent doesn't know anything. And even though the shape, the trend of the error is very similar in both, the agent is able to highlight those regions where the error is high. And in fact, the order of magnitude is very similar between the estimation and the real error. Well, for the same problem, also we ran several simulations with uniform polynomial order. And as you can see, using p-adaptation, the number of degrees of freedom and the computational cost is smaller than even using a uniform P2. But the error is also smaller. So the cost is smaller and the accuracy is higher. And of course, if you want even more accuracy at the cost of more computational time, you can tune the parameters of the reward function to obtain an agent that fits to your needs. Also, we tried with a cylinder at Reynolds 200, and on the right, you have a snapshot of the average polynomial order in each element, where dark colors mean high polynomial orders, and light colors mean low polynomial orders. So as you can see, far from the cylinder and far from the wake, the polynomial order is always the minimum because nothing of interest is happening, and only in those regions where we have the vortex shedding or the boundary layer around the cylinder is where the agent is increasing the polynomial order. And on the left, you can see how this adaptation is dynamic. We are adapting all the time to capture only those regions where we have strong gradients. And well, we compared the results for the lift and the drag with our approach and with different state-of-the-art solutions just to check that our method is accurate. Also, we tried with a cylinder at Reynolds 13900. Again, on the top right, you have the average polynomial in each element. And again, high-order polynomials are only near the wake and near the cylinder. But again, it's a dynamic adaptation. That's why on the left, you have a plot showing only those elements where high-order polynomials are being used. And as you can see, the high-order elements are changing all the time to capture all the turbulent fluctuations that may appear in the flow field. And far from that region, the flow is not turbulent, and that's why the agent selects a low-order polynomial. And on the bottom right, you have a histogram showing the percentage of elements that are adapted with P2, 3, 4, 5, and 6. And the most important thing is that most of the elements are adapted with the minimum, P2. That means that we are saving a lot of computational time. And the P5 and P6, the high-order polynomials, are only used where required. And also, as I said before, our algorithm is anisotropic, and that's why we have different bars for the three different axes, X, Y, and Z. Then to test the laminar to turbulent transition, we run the same problem that Esteban explained before, the Taylor-Green vortex. The first row is the velocity magnitude, and the second row is the average polynomial order in each element. And this case is very interesting because you may notice that those regions where we have strong velocity gradients are the same regions where we have high-order polynomials. So the agent is capable of understanding that it's important to capture strong gradients, and that's where the agent increases locally the polynomial order. As the time increases, the flow field becomes more and more turbulent, and that's why the overall polynomial order is increased in the whole mesh. This behavior is what is represented in the figure on the left, where the average polynomial in the whole mesh progressively is increased towards the maximum polynomial order P6, because the flow field is fully turbulent. And on the right, you have the kinetic energy rate solved with a polynomial P3, 6, p-adapted, and a DNS simulation. As you can see, the P3 is not accurate enough, but the P6 and the p-adapted simulations are almost the same, and both are very, very close to the DNS simulation. However, to compute the P6 solution, it took around 100 hours, while the p-adapted with the same computer, same configuration, same everything, it only took 41 hours. So to obtain almost the same result, we are saving 60% of the computational cost. And finally, to show you a huge problem to use p-adaptation, we solved an offshore wind turbine. And I selected this snapshot because the wake is still developing, so that you can see the different colors for different polynomial orders. And here we mix everything that Esteban explained before. We are using actuator lines for the blade. We are using immersed boundaries for the tower, the nacelle, and also the waves. And we are using p-adaptation. And here, as you can see, far from the wake and far from the blades, the polynomial order is the minimum, which is 1. But where in those regions where the wake is developing and the flow field is turbulent, the polynomial order is increased. And please look at the detailed view, the zoom in, and there you can see how inside the waves, where we are using an immersed boundary, and so the velocity is 0 or almost 0 all the time, the reinforcement learning agent has decreased the polynomial to the minimum automatically. The reinforcement learning agent doesn't know what's the meaning of wave or what's the meaning of immersed boundaries, and even though it's capable of understanding that if nothing relevant is happening there, then I have to decrease the polynomial order. And here I want to highlight again that for all these results that I have shown you, we have trained only one reinforcement learning agent, and it's the same for all the different cases. And we are solving different equations, we have different meshes, and of course, different boundary conditions. And finally, we wanted to test our error estimator for this problem. The first row is like the maximum error estimation, and the second row is like the average, okay? And here, again, the agent doesn't know what we are trying to solve on what are the critical parts, but it is able to highlight those points that we as engineers expect to have a higher error. In this case, the agent has highlighted that the error is higher near the actuator lines, where we have the blades, on the no-slip wall boundary condition on the floor, because the elements are very big and we are not able to accurately capture the boundary layer. Also, inside the immersed boundaries, inside the tower and the nacelle, because again, the elements are very big, and inside the wake, because we have a fully turbulent flow. So all these elements are critical, because that's where we expect to have higher errors, and the agent, without knowing almost anything, it's capable of highlighting those regions and also to quantify those errors. And well, that's all regarding the results. So what's the ongoing work on this topic? We are working on use reinforcement learning and p-adaptation for moving immersed boundaries, also for acoustics to increase the accuracy for those problems that are not easy. Of course, we are comparing with different state-of-the-art p-adaptation algorithms to check if our approach is better or not. And finally, we are working on a dynamic load balancing to improve MPI parallelization. And well, we have written 2 papers on this topic. You have them, the QR codes on the right. The first one on the top is the original idea, very simple for one-dimensional cases only. But the second one, we uploaded this one to arXiv just some weeks ago, and it's the full explanation of how to do anisotropic p-adaptation for three-dimensional problems with turbulence, with error estimation, and everything. And well, finally, just one more slide to conclude. First of all, we have discovered that reinforcement learning for p-adaptation leads to a very, very general approach, and it allows to improve the accuracy, but at the same time to reduce the computational cost of CFD simulations. This methodology can be potentially applied to any partial differential equation and any computational mesh, because the agent is going to adapt inside each element independently. Also, the reinforcement learning agent has to be trained only once and for all, and it is trained with one-dimensional cases. That's why the training is so fast. And as I said before, the training is also decoupled from the solver. Even though it's trained in these conditions, it's capable of adapt and accurately solve 3D turbulent simulations. And finally, with this approach, we are able to provide a very, very cheap estimation of the spatial error in each element of the mesh. So, as a final remark, we can say that reinforcement learning can be applied to minimize manual intervention, to improve the accuracy of numerical simulations, and finally to speed up your CFD code. So that's all. Thank you very much.